So thanks for being here. In a few months, NASA's Kepler mission is going to launch, and that's focused on detecting extrasolar planets. And to talk about his part in that mission is Travis Metcalf from Boulder, Colorado, from the National Center for Atmospheric Research. And he's also going to touch on a project he's involved with called Pale Blue Earth.
Thanks for coming. Thanks for the invitation. I've tried to make this presentation accessible at a public level because I'm aware that it's going to go out on YouTube. So feel free to interrupt with questions at any time. You may have seen this image in the news in the last couple of months. This is the first direct image of an extrasolar planet, a planet orbiting a star other than the sun. Several years ago, the Hubble Space Telescope took an image of this star and discovered a dust ring, a ring of dust around the star. And the fact that it was a ring rather than a disk, given what we understand about the formation of planets, suggested that there may be a planet in this system at the inner edge of the ring that had swept out the material in the inner portion of the disk. So a couple of years later, they went back and took another image, hoping that that planet would have moved. And sure enough, they found a slight motion of the planet over that 2-year period. Now, this planet is several times the mass of Jupiter, and it orbits its star several times further away from its star than Neptune is, like 3 times the distance of Neptune from the sun. What we'd really like to find, of course, is the holy grail in this field is an Earth-like planet in orbit around a sun-like star. And I guess the reason that that's the holy grail is that we really want to answer this question, are we alone in the universe? And so what we're really after is habitable planets, other planets that are orbiting at Earth's distance and that have a mass similar to the Earth. To accomplish that objective, what we need is very precise measurements of the amount of light coming from a very large sample of stars, say 100,000, over a several-year time span. And the reason for that is that if we look at stars for a sustained period of time, what we'd like to, there are some fraction of those stars that will have planets, and some fraction of those planets will be oriented in such a way that the planet will pass in front of the star from our point of view. And that will cause a small dip in the amount of light that we see for a short period of time, a couple of hours. And the depth of that dip is a measure of the relative area of that planet compared to the area of the star. Now, in general, we don't know the sizes of the stars that we'd be looking at. And so in order to get an absolute size for the planet, to know if it's exactly the size of the Earth or twice the size of the Earth, we need some way of measuring the absolute size of the star that it's orbiting. And that's the main thing that I'll be talking about today. So NASA's Kepler mission is going to launch about 2 months from now. The main goal of this mission is to find habitable planets around sun-like stars. To accomplish that objective, it will look at this enormous single field of view in the sky. It's about 400 times the size of the full moon. And it will just stare at this single big patch of sky using very high-quality digital cameras, taking measurements of the brightness of about 100,000 stars every 30 minutes for about 4 to 6 years. The thing that drives the timescale is that to find Earth at Earth's distance around a sun-like star, you need to see a small dip in the amount of light, wait an entire year until the planet comes around again, and find an identical dip in the amount of light, and then a third time to make sure that the period is the same. There are many things that could produce a false detection of if you just have 2 transits, say a sunspot or something like that. So 3.5 years is about the minimum amount of time that you need to monitor the stars in order to find Earth at Earth's distance. So to determine the absolute size of the stars, and therefore the absolute sizes of the planets that are discovered, a small fraction at any one time of those 100,000 stars will be monitored at a higher cadence. We'll take a measurement of the brightness every minute instead of every 30 minutes. And that sampling is sufficient to see oscillations in the amount of light in the star itself. Stars naturally pulsate very, very subtly, a few parts per million in their total integrated brightness. And those oscillations can tell us quite easily the absolute size of the star, and therefore the absolute size of the planet. This image is a snapshot of the part of the Kepler target list in Google Sky that we're using as part of a public education and fundraising project called the Pale Blue Dot Project. And if you want to know more about that, ask me at the end and I'll tell you a little bit about it. But what I'd like to do now is give you just a broad overview of how we can learn anything about the insides of stars using their pulsations. And then talk about the specific low-level form of artificial intelligence that we're using to try to do this in an automated way. The amount of data coming from the Kepler satellite will be so immense that we just can't possibly keep up with that amount of data without automating the procedure. So I'll talk briefly about... the amount of data will be full astroseismic information, so the pulsation frequencies of hundreds of stars every 3 months for several years. So to put that into perspective, in the last 5 years, such measurements have been made on maybe a dozen stars. So the volume of data will be much, much greater. So I'll talk about asteroseismology. I'll talk a little bit about the genetic algorithms and how we're using them to automate this procedure. And finally give you the first results of our first application of this automated method to a star that we know and love, the Sun.
One more question, like where does this point, where is this region in space that the telescope will be looking at?
It's this 100 square degrees near the plane of the Milky Way, in between the constellations Cygnus and Lyra.
How was it selected?
It was selected to be close enough to the galactic plane that you could find 100,000 solar-type stars to monitor, but far enough out of the plane that you won't get as much contamination from very large stars that are less interesting from the standpoint of extrasolar planets. Yeah.
Just repeat the question so sure.
Yeah. Okay. All right. So one of the earliest works in the theory of stellar pulsations, or the oscillations of stars, was written in 1926 by British astronomer Sir Arthur Eddington. And this is the way, the book was called The Internal Constitution of the Stars. And this is the way that the book begins. At first sight, it would seem that the deep interior of the sun and stars is less accessible to scientific investigation than any other region of the universe. Our telescopes may probe farther and farther into the depths of space, but how can we ever obtain certain knowledge of that which is hidden behind substantial barriers? What appliance can pierce through the outer layers of the star and test the conditions within? Well, 80 years ago when this was written, Eddington's answer was theory. Theory is how we'll create mathematical models of stars, and that's how we'll learn about their interiors. But 80 years later, we now have a different answer. Asteroseismology. So asteroseismology is the study of the internal structure of stars using their oscillation or pulsation frequencies. Basically, it's analogous to seismology on the Earth in that we use sound waves that probe through the interiors and bring information to the surface in the form of brightness and velocity variations, surface motions. One of the main motivations for wanting to know about the insides of stars is that stars are essentially working nuclear fusion reactors, and we have one at the center of our own solar system that we've been studying for 30 years. If we could somehow master the form of energy production that the sun and all the stars use, we would have an inexhaustible form of clean energy for the planet with no radioactive byproducts. So that's the grand scheme. We've been studying the sun, as I said, for several decades in this regard, a field called helioseismology. But the sun is just one star at a particular set of physical conditions at a single age in its evolution. And to try to ensure that we haven't fine-tuned our knowledge our understanding in some way to fit this single point of the sun, it's useful to study other stars that are like the sun, say, that sample different physical conditions and different evolutionary stages of stars to make sure that we haven't fine-tuned our knowledge. And a more immediate concern is that the sun consists of boiling gases with embedded magnetic fields. These bubble up to the surface. The magnetic fields get twisted and break and send huge ejections of material out, sometimes towards the Earth. And these ejections of charged particles can be a danger to astronauts on the International Space Station, can damage satellites, and can induce currents that bring down electrical grids on the Earth. So from a practical standpoint, it would be nice to know what's going on the inside so that we can learn to predict these sorts of events in our own sun. Well, here's a very intuitive example of how we can use sound to see inside objects that are normally opaque. Like the Earth, the sun and other stars are opaque. The hot surfaces are opaque to radiation. We can't see down into the interiors directly. But it turns out that they have their own source of sound waves that we can use to probe the interiors. If you look at a small patch of the sun over time, and this is a time-lapse movie, so it's sped up quite a bit, and you see the Earth here at the same scale to give you an idea of how small a patch of the sun we're actually looking at. If you look at the sun's surface, it's just boiling. There's these boiling motions, upflows and downflows. And if you convert these motions into sounds, you'll hear something like this. Basically, this boiling is creating sound waves at all frequencies, at a wide range of frequencies. And some of these frequencies are resonant inside the spherical cavity of the star and set up standing waves, coherent oscillations that we can use to probe the insides of the stars. They travel through the interior and bring information to the surface, and we can study it there. The convective motions are a little bit like a piston. So they're driving density waves, these sound waves, pressure waves, through the interior of the star. The speed of sound inside of a star depends on such things as its temperature and its composition. And so we can use those sound waves to actually probe those quantities. Since the temperature of a star increases as you go farther and farther in, the leading edge of any wavefront of sound waves or pressure waves that are moving down towards the center of the star, the leading edge is deeper into the star and will have a higher sound speed. And it will gradually refract or bend away from the center of the star and back up toward the surface. And when it hits the surface, it essentially just bounces off and back down into the center of the star. And this is how these standing waves are set up. Now, the sound waves that are generated in stars are much, much lower than what the human ear could ever hear. And the sound waves themselves are only generated and travel inside the star. The space around the star is an empty vacuum, and sound waves can't travel through the empty space between us. And so it's only through the variations in the brightness at the surface of the star that we use to determine the presence of these sound waves on the interior. The sound does not, it's important to realize that the sound does not directly travel to us, and we're not actually listening to the stars. We're converting the variations in the amount of light into sound waves. Now, to do that in a way that the human ear can appreciate, you need to speed up the sound waves by a factor of about 1 million. So there are lots of things that here on Earth that generate sounds that are beyond the capabilities of the human ear to hear. For example, at the low end and slightly below the range of human hearing, blue whales have songs that some people find very beautiful. I'm not sure what they're saying. I think they might be complaining about the Navy sonar or something. But if we speed up the sound waves that we record underwater of the blue whales, we can map them into the audible domain and hear a sound that like the one I just played. Similarly, bats emit high-frequency sound waves as a form of sight, basically, that are above the range of human hearing. But if we slow those sound waves down, we can also hear them. And I'll warn you that this is a slightly disturbing sound. So that's how that's speed. All right. So we'll do similar things for stars in a few minutes. But the basic idea, before on the way there, let's just talk in general about oscillations and how we characterize them. And we'll start with a simple example of oscillations in one dimension. And a good example there is the string of a violin. So there's essentially a single number that can characterize the oscillation on the string of a violin. And that is, it represents the number of times that the string wobbles back and forth between the two endpoints. And the frequency of the tone that the string emits is a function of that number. So the more times the oscillation oscillates between the two endpoints, the higher the frequency of the sound that we hear. So these are a few examples of some of the lowest order oscillation modes in a violin string. The frequencies that you hear and the geometry of the oscillation mode essentially tell you something about the mean density of the string and the overall size of the instrument that's playing it. So the human ear can easily distinguish between something like a violin and something like a cello. Okay, let's move to two-dimensional oscillations. Here, the oscillations divide into two broad categories. In one category, the radial modes, the oscillations are symmetric about the center of the drum. So again, you can describe those types of modes with the number of times the mode wheels back and forth between one side of the drum and the other. And again, they are, the tone that you hear from such a oscillation mode will depend on that number, so the frequency is higher for higher numbers. The non-radial modes are not symmetric about the center of the drum, and instead the energy of the oscillations seems to move from one side to the other, back and forth. And this pattern of how the oscillation energy moves about the surface of the drum is another number that tells us about the geometry of the oscillation mode, and also helps determine the frequency that we actually hear. So again, the information that we get from the frequency and from the geometry of the oscillation mode off the head of a drum tells us something about the average surface density of the material on the top of the drum, as well as the overall size of the drum. So we can easily distinguish between something like a bongo and a big kettle drum. All right, now to 3D oscillations, and this is where stars are the perfect example. Again, we have the separation into two broad classes of modes, the radial modes and the non-radial modes. The radial modes from the outside of a star look like the star is just breathing. Everything's getting expanding and contracting. You see the star's surface uniformly get brighter and fainter. But if you look on the inside, you find that the oscillation actually does wiggle back and forth a different number of times on its way from the center of the star to the surface. So some parts are expanding while other parts are contracting. It's not just a uniform expansion and contraction like a breathing motion necessarily. The non-radial modes again show the characteristic behavior that the oscillation energy is moving from maybe one side of the star to the other, and this pattern on the surface, the geometry of the oscillation that we can actually observe, tells us something about the frequency of the oscillation mode. And these are some of the lowest order patterns that we can observe in other stars because the so-called dipole, quadrupole, and octupole modes have very large features so that when you average over the whole surface of the star, which we must do with distant stars, we don't have any spatial resolution across the surface of the star. They're just too far away. So in the case of the sun, you do have spatial resolution. But when we're looking at other stars, we're just looking at an average of everything on the surface that's pointing towards us. So it's only these lowest order non-radial modes that we can see. So we see the radial modes and these lowest order non-radial modes. Yeah?
Why does the brightness change as the star pulsates? Because the energy output is constant, I assume. So.
That's right. Remember that these sound waves are essentially pressure waves. And so as we're changing the pressure on different parts of the surface, those different parts, one part heats up while another part cools off.
So it's an actual change in brightness.
It is an actual change in brightness. And in stars like the, sorry, I should have repeated the question. In stars like the sun, these brightness changes are measured in a few parts per million. There are very, very tiny oscillations in the amount of light. So the sun, for example, you can see the whole surface get brighter and fainter with a period roughly 5 minutes. Every 5 minutes, you'll get a brightening and a fainting, but at this very subtle level. So what do we actually measure from a distance? There are two different possibilities for how to measure these oscillations in stars. There's the light variation, and that's the method that we use, that the Kepler spacecraft will use, because the total light variations are so small, as I mentioned, parts per million, that the turbulence, the scintillation noise in the Earth's atmosphere just completely washes it out. So there's no hope of measuring those brightness changes from ground-based telescopes. You have to do it from space. In this top plot, you're actually seeing oscillations in a star like the sun, similar to the sun. You see the full range here is less than 0.5%. And the very largest oscillations that you see in this star monitored over nearly 2 months, those oscillations or those variations are actually due to just tiny star spots rotating into view and out of view again sometime later. Those are not the oscillations that we're looking at. What looks like noise, the thickness of this line, is actually mostly due to those boiling motions themselves. And the tiniest effects that you can't even see at this scale are the actual oscillations. But by decomposing this signal into its constituent frequencies, you can separate out those effects and see the oscillations clearly. The other possibility is to measure the surface motions that are caused by these pressure waves. These are measured in just a few meters per second. It's just the material on the surface moving on average towards you or away from you. And we can measure this by passing the light through a spectrograph and looking at the dark features that are created by the individual chemical elements in the spectrum and the rainbow. And those dark lines move back and forth in frequency as the source moves towards us or away from us. So we can measure that radial velocity to document those variations. And this, in fact, has been the primary method that extrasolar planets have been detected by, because a star with a planet in orbit around it will have a reflex motion. So if you have a Jupiter out here, it's not just that Jupiter is orbiting the sun, it's that the sun and Jupiter are orbiting a common center of mass. And so as the Jupiter goes around the star wobbles a little bit. And you can measure the radial portion of that wobble using this method and thereby infer the presence of extrasolar planets. And this is by far most of the couple of hundred extrasolar planets discovered around other stars have been inferred from this sort of technique. And in fact, that's what's driven the technology to get very, very precise measurements of the radial velocity that finally, just in the last few years, it's precise enough now to measure the oscillation motions on the surface of this star. Okay. So let's look at a few examples of the oscillations in a few different types of stars, just to give you an idea of what they're all about. So the nearest system of stars to the sun is the Alpha Centauri system It's actually a collection of 3 stars in orbit around each other. One of the stars is slightly larger than the Sun, another is slightly smaller than the Sun, and the third is just a tiny red dwarf star called Proxima because it's at the moment actually the nearest star to the Sun. So Alpha Centauri A was observed some years ago using this radial velocity technique from the ground. And if you look at essentially the amplitude or the power of, say, the volume of the oscillation as a function of its frequency, if you decompose those signals out into their constituent frequencies, you see a whole range of frequencies with discrete values between about 5 and 10 minutes excited in Alpha Centauri A. And if you convert those frequencies into the audible range by speeding them up by a factor of 1,000,000 or so, you would hear something like this. So these oscillations tell us about the size, the mass, the chemical composition, even the efficiency of convection in these stars, and their ages, which is another thing that is very difficult to measure for individual stars and will become much more easy to do using the technique of asteroseismology. Now, towards the end of its life, our own sun will slowly expand into a red giant star. This is a simulation of convection in a red giant star done at the University of Minnesota. You can see the convective cells are much, much bigger, occupying a significant fraction of the surface of the star compared to the movie that I showed you earlier. And when you translate these oscillations again into the audible domain, you'd hear something like this. All other things being equal, a bigger star will oscillate in lower oscillation frequencies. When these observations were actually taken, and a press release was issued with this very exciting result of one of the first detections of solar-like oscillations in another star, the investigators released this sound file along with the discovery press release, and one of their collaborators was in Belgium, and their students reported that very weekend the discotheques the DJs were already incorporating this sound into their music. So if anybody ever tells you that there's no practical application of astronomy, you can tell them otherwise. Finally, at the very end of our sun's life, all that will remain is the hot, dense core of what used to be the red giant star, a white dwarf star. And this is one example of, at the very, very end of a white dwarf star's life, it actually is at such high pressure that when it gets cool enough, it will begin to crystallize in the center. And so at the very, very end of our star's life, there will just be a big, hot crystal at the center of the solar system. This particular star, BPM 37093, is oddly a little bit more massive, and so more massive than an average white dwarf star, and so actually begins to crystallize at a temperature where those stars are known to pulsate. And so by studying the pulsations, you could actually detect the presence of this crystallized center in the white dwarf star. And again, if you translate these oscillation frequencies into a sound, you hear something like this. Again, all other things being equal, a smaller star will oscillate at higher frequencies. So I think you get a general sense that by observing the oscillation frequencies in other stars, we can get some idea about its absolute size. It's sort of one of the first things that comes out, just from the range of oscillation frequencies that it exhibits. And remember, the motivation here is that if we know the absolute size of the star, then the measurements of transiting planets will allow us to convert the relative radius of the planet compared to the star into an absolute size for that planet. So let me just take a step back here now, change gears, and talk about, now that we are beginning to get these observations of oscillations in other stars, how do we translate those observations into actual knowledge about the star? The general way that this is done in science in general is that once you have the observations, you create a computer model, a mathematical model. That's what Eddington was talking about 80 years ago. And in general, your model is not going to be perfect the first time. So you look at the differences between the model and the observations, and you try to adjust whatever parameters or geometry or physics of the model to try to get a one-to-one correspondence between the observations and the model output. And this process of sort of revising the model to try to improve the match to the observation, really, fundamentally, that's an optimization process. And what role does aesthetics play? It's sort of like, one example is during Copernicus's time, there were competing models of the structure of the solar system. Once they realized that the Earth was not at the center of the solar system and the sun was actually there, there were competing ideas that, well, the orbits of the planets could be ellipses, or they could be perfect circles with perfect circles on top of those perfect circles, epicycles they called them. And from the standpoint of aesthetics, they both made equal predictions, but one is simpler. And so you'd prefer, it's like Occam's razor, you'd always prefer the simplest. Okay. So mathematicians have devised various methods to deal with optimization problems, each with their strengths and weaknesses. Let's imagine that this surface represents two different parameters of your model on the two axes, and the height of the surface represents the quality of the match between the predictions of the model with those parameters and the observations that you have in hand. Now, if your parameter space, if you like, looks like this, then pretty much any optimization method that you want to use will work just as well. You will select some initial guess of those two parameter values, which will be somewhere in this parameter space, and then you'll iterate in some way to try to improve upon that first guess. And the most likely outcome is that you'll, if your optimization method is good at all, you'll find this single peak in the parameter space. But what if your parameter space looks like this? Then the problem becomes a little bit more tricky. If you give an initial guess for the parameters, the most likely outcome is that you'll end up at a local optimum rather than the global optimum right in the middle. Now, if you just calculate all of the models for each combination of all of these parameters, you can construct a map of the space and know exactly where the global optimum is. But the whole point of an optimization method, in some sense, is to avoid having to do that. So that motivates our use of a genetic algorithm, which you can think of as exploring the space as broadly as a complete grid of all the parameters, but with a substantial discount. Essentially, a genetic algorithm is an iterative Monte Carlo technique with a kind of a memory of what has worked better than average in the past. Excuse me. Here's how it works. You populate your parameter space with some number of random combinations of the parameters. And you evaluate the model for each of those combinations and calculate the height of that surface, the difference between the predictions of the model and the observations that you're looking at. And you assign a fitness, a goodness of fit, to each of those trials that is inversely proportional to that quality of the match. So, or to the inversely proportional to the difference between the observations and the model. So if it fits well, it gets a higher fitness. If it doesn't fit so well, it gets a lower fitness. Then you select a new population from this old initial random set of parameter values from the old one, weighted by the fitness. So things with high fitness have a better chance of passing their characteristics on to future generations. Now, without something else, without another ingredient, you would never find a solution that's better than the best in your initial sampling of parameter spaces. So you need some way of mixing up the information in some way And a genetic algorithm uses a series of operations that are analogous to breeding and mutation. So that's where the genetic part of it comes in. It's an analogy with biological evolution through natural selection. So you mix up the information from that newly selected population, and you go back and evaluate the model of those now shuffled up solutions and continue iterating like that until you've essentially stopped improving your match to the observations. Now, all of the details really are in these operations that mimic breeding and mutation. So let me just spend a little bit of time telling you how that works. So suppose you have two parameters in your model, and you pair up. The first thing you need to do in order to apply these operations is to encode them in some way. And so the simplest way of encoding would be to just take the numerical values of the parameters and convert them into a long string of digits. This string is analogous to a chromosome, and each digit is analogous to a gene. Okay? So then the breeding operation randomly pairs up these encoded representations of the parameter sets. And then to breed, you randomly select a position along the string, chop the strings at that position, and swap the two strings from that position to the end. So this is analogous to breeding. The mutation operation is you randomly select a position along each of the strings and then change that value to a new randomly selected value. That's like mutation. So once you've performed these operations on all of the whole population, you then decode the strings of numbers back into actual values for the parameters. And you can see in this example, the final set of the new set of parameter values is related to the original set in an extremely nonlinear way, a very stochastic, random way. There's a sound theoretical basis for why this particular combination of operations leads to optimization. It's called schema theorem, but I honestly don't understand schema theorem, so I'm not going to explain it to you or even try. So that's how it works in theory. How does a genetic algorithm work in practice? There's a famous story about Francis Crick, the co-discoverer of DNA, who gave a talk about evolution and DNA. And at the end of his talk, one of the members of the audience stood up and said, "I just can't see how evolution could possibly create something as complicated as an eyeball. How do you explain that?" And his response was, "Well, my dear, evolution is cleverer than you are." That really summarizes why we use genetic algorithms, because they work. They just work. So here's an example of the initial random sampling of a space of two parameters, say the mass of a star and its temperature. And if we let the genetic algorithm go and iterate through this process, wow, that was fast. Let's wait for it to cycle through. What you see is a relatively fast initial convergence to a single point in this diagram. But then after it gets to a relatively confined region, the genetic algorithm continues to try to innovate. So you see the signatures of those two genetic operators in this diagram, in that around the point where many of the solutions fall, you see a kind of a crosshairs appearing pattern. And that's the mutation operation. The mutation operation, remember, takes a single position along that string and randomly changes the value. So it's just changing the value, smaller or larger, of one of the parameters. And so you get jumps in one of the parameters at a time. The crossover operator can change the values of two parameters at once, because depending on where it decides to cut and splice the chromosomes, if you like, this can lead to diagonal jumps in the parameter space. And so you also see some larger or smaller jumps in the diagonal directions in this diagram. All right, now to the final topic, how are we actually using genetic algorithms, this sort of low-level form of artificial intelligence, in the context of trying to model stars and match our theoretical models of their oscillation frequencies to the observations that we'll soon get from the Kepler satellite.
Question. On this genetic algorithm, is actually a situation where it doesn't find the optimum, where it just kind of, the way the optimum is put, it just doesn't find it, it converges somewhere else, which is not the optimum?
Yes, I mean, the genetic algorithm is a stochastic process, and so if you run it forever, it will always find, almost always, you can contrive specific mathematical forms for the parameter space that will deceive it or make it extremely inefficient. But if you run it forever, it will eventually most likely find the answer. Okay. So the traditional approach to the task of modeling stars is to take some non-seismic observations, say measurements of its total brightness, its colors that are an indication of its temperature, and these define a kind of a box in this parameter space here. And these tracks are models of stars that start their lives over on one side and then evolve. So the star is changing its total brightness and its temperature over time. And for a given mass of the star, you'll get a nice track in this diagram for each stage of that star's life. So the idea is that you adjust the value of the parameter, say the mass, to try to pass through this box of classical non-seismic observations of brightnesses and colors. What asteroseismology does is at each point along these tracks, you can also take that model and perform a pulsation analysis on it. And so it provides a kind of a third dimension to this figure so that not only must you pass through the box, but the oscillation frequencies of the model in that particular point must also match the oscillation frequencies that you observe. So it provides many, many more new constraints that we didn't have before to find the optimal match between your stellar model and the observations. Now the good and bad thing about the Kepler mission is that it will be producing data at such a rate that we just can't possibly try to keep up using this traditional adjust the models by hand and hope for the best. So what we really need is a general purpose tool that will probe all of the values of the parameters where we expect to find solar-like oscillations in other stars. So a whole wide range of masses for the stars, of compositions, and here even of ages that are represented by the position in this diagram, and even the efficiency of convection. And the basic idea here is that you take the oscillation frequencies that Kepler observes, and you feed them into this stellar modeling pipeline that is driven by the genetic algorithm. Oscillation frequencies in, let the genetic algorithm go to work, and get the optimal values of those parameters out as output. It's a computationally intensive problem, but humans don't have to be involved except to start the thing up. For our first application, we're using data from the BISON network. BISON stands for Birmingham Solar Oscillation Network. It started a project to establish a global network of telescopes because the Earth's rotating. If you want to observe the sun 24/7, you need a network of telescopes around the globe. And this was started more than 30 years ago and doing helioseismology, seismology of the sun, for quite a long time, very precisely. The nice thing about this data set is that the duration, the length of the time series, and the precision of the time series are comparable, in fact even better than what we expect for other sun-like stars from the Kepler mission. And so we can degrade the observations so that they'll match the uncertainties that we'll get from the Kepler observations, and then test if we feed those oscillation frequencies to the genetic algorithm, does it find the actual properties of the sun? And we have the advantage with the sun that we know those properties extremely well. They've all been measured very, very well, including the age. You can determine the age of the sun or the solar system just from the ages of meteorites, for example. So here's an example of how the behavior of the genetic algorithm on this BISON data set. You can see what we're looking at here is a measure of the difference between the model, the best model in a particular iteration of the genetic algorithm, and the observations as a function of that iteration or generation number. And you see in less than 200 generations, this is for 4 independent runs of the genetic algorithm, seeded with a different random initialization. You can see that initially the convergence is quite fast. That's driven by the breeding or crossover operator. And then that's followed by a series of discrete jumps, improvements in the fit from random favorable mutation operations. And you can see that 3 out of the 4 runs find the global solution in under 200 generations. And we actually ran these simulations for 300 generations, and there was no further improvement. So the idea here is to optimize our efficiency, so cut it before we stop improving. As I mentioned, if you run the genetic algorithm indefinitely, it will eventually find the global solution. But a more efficient way is actually to run it for a finite amount of time, but just do several simulations with different random initialization, and you can end up getting the global solution in fewer model evaluations than you would by just running one forever. So that's how the genetic algorithm did. It takes 10,000 CPU hours for each of these runs, so it's a pretty computationally intensive problem. We've been doing it on a single rack blue gene system at the National Center for Atmospheric Research. And here are the results. When you put the sun's oscillation frequencies into the genetic algorithm, this is how it did. So here we're looking at the frequency of the oscillation versus basically a measure of its geometry. So here we're looking at the radial modes, dipole, quadrupole, and octupole modes. And in fact, we only fit the 36 frequencies that lie between these dashed lines, and we did not actually use as constraints these octupole modes. So fitting only the L equals 0, 1, and 2 modes in this range, you see that the match is really, really quite good, and that it also matches the L equal 3 modes and the modes that are outside the frequency range at the low end for all of those modes. So in terms of matching the frequencies that we actually observe in the sun, the genetic algorithm does very, very well. And looking at the more traditional observational constraints, like the total brightness and the temperature, the surface temperature, you see a typical error box here for how well those parameters might be constrained for objects that we will see in the Kepler satellite. And the dot there is the solution that the genetic algorithm found. So not only does it match the oscillation frequencies, but it matches the temperature and age within a very high precision, and the total brightness and the radius, the key to finding the absolute size of the planets, to very high precision. So it's a very encouraging first result. Put the sun's oscillation frequencies in, and we get the sun's properties out. And so now our task is to repeat this sort of experiment for stars in other regions of the diagram where maybe they're more massive or less massive or older or younger, and make sure that it can fit those stars as well. And what we'd like to do, what we're working on, is actually making this tool, this pipeline, available as a TeraGrid science gateway, so tied to computational resources, so that our collaborators, many of them in Europe who don't have access to their own supercomputer, can go to this web interface, upload their particular set of observational data from the Kepler satellite, click a button, and the genetic algorithm will run on some computational resources in the US, and a week later they'll get an email with the solution. It'll also be archived to the website to avoid duplication of effort. And of course, the website will also allow people, it's all open source, so people can, if they do have their own supercomputers, can run this code on their own. the basic idea here is to encourage a uniform analysis of the Kepler data so that when we're looking at these hundreds and hundreds of stars every few months, the tools that we're using to analyze them could be the same for all the sets of data. So any things that we want to infer about the population of stars that the Kepler satellite looks at will be self-consistent, internally self-consistent. So it's a great first success. If there's one thing hope you'll take away from this talk, it's the answer to Eddington's question. What appliance can pierce through the outer layers of a star and test the conditions within? I hope you know now that the answer is asteroseismology. Thanks. Any questions?
Do you want to talk about the Kepler dot project?
Sure. So we're working on a public education and fundraising project to fund this asteroseismology part of the Kepler mission. Basically, the consortium of investigators who are in charge of this part of the mission are headquartered in Denmark, and so NASA simply cannot fund that part of the project. It's not legal for them to fund a foreign institution. And so, as an alternative, we're starting this program where members of the public can adopt one of the 100,000 stars that the Kepler satellite will look at for a donation of $10. They get like a personalized certificate by email, and then when planets start to be discovered around the Kepler stars, they'll get an email saying, oh, look, your adopted star got a planet around it, and a link to information about where they can learn more about the discovery. The idea here is to, there are many companies on the internet who have these deceptive name a star programs, and we're actually we're funded by the Google Grants program for AdWords advertising, and so we're competing side by side with these companies, giving people a nonprofit alternative to actually have their money support scientific research rather than just lining the pockets of these companies that are doing it. So the basic idea is people select a star using Google Sky, so they can go in and browse the target stars interactively in Google Sky, click on the place mark and find the number, and then say, I want to adopt that star. And the place mark will then say who it's adopted by. So no two people can adopt the same star. That's an important feature as well. They could also choose from a special text version of the catalog, maybe select a number that signifies a special date, or look at the physical properties of the star to try to make it as sun-like as possible, maybe give it a better chance of having planets around it. And then, as I mentioned, they get a personalized certificate by email and information once Kepler starts discovering planets. So far we've raised less than $10,000, but we're really hoping to get some kind of exposure to get people excited about this project. It really is a cool thing. So.
Probably offering some real estate on...
Offering some real estate on the planets, yeah. Or mineral rights or something, yeah. Yeah.
So I was a little bit curious about your computational costs. With 10,000 CPU hours, 100 generations, 100 models running at once, like 1 CPU hour per model?
So the question is about the computational costs of the genetic algorithm. So the Blue Gene, as you know probably, is a special architecture that uses slow processors like 700, 800 megahertz in order to pack them in small enough space. There's 2,000 in a single rack. But part of it is just the unavoidable cost of evaluating a lot of models. It's comparably global to just calculating all the models in the space. It's a 5-dimensional space to begin with. But it's about somewhere between 100 and 1,000 times more efficient So you're only evaluating less than 1% of the models that you would have to evaluate for a full grid of that space, but it's a big space, so less than 1% is still a lot of models. That's really
So
the
for
answer.
the full Kepler data, will it make more sense to just evaluate them all since you're going to be, all over that space to begin with?
So why not just evaluate all the models and use the grid over and over again for all those stars? The main reason is because when you calculate a grid, the physics that you use in the models is frozen in. And we want to have the ability to gradually improve the models over time so that we expect that when we start looking at oscillation data in other stars, we're actually going to learn something our models aren't going to fit, right? And so we're going to have to make changes to the constitutive physics, to the ingredients of the models to try to remedy that, basically. And so that's the main motivation, is since the grid freezes the physics and we really want the flexibility to improve things over time.
I have several questions. It's very interesting that you're using genetic algorithms. I was wondering if you could talk a bit about the relationship between the number of inputs to the model, the number of outputs, and how many 3D parameters are you trying to tune inside the model?
So the question is about how many parameters it's feasible to use the genetic algorithm to tune for this type of optimization. I've successfully used a genetic algorithm for stellar models up to about 6 or 7 parameters, but not more. As the parameter space gets higher and higher dimensional, it gets harder and harder. The genetic algorithm is a less efficient method.
Like some gradient descent algorithms like neural networks?
No, I have not tried neural networks. What we're actually developing now is a kind of a hybrid approach where we use the genetic algorithm to narrow in on the region of parameter space to assure that we're in the right local maximum, and then use a more traditional gradient climbing method to narrow in on the precise values and uncertainties. And that, I think, has the potential to improve the efficiency of the approach.
So just a question about the details of your genetic encoding. Does it make a big difference whether a parameter is, a raw observable quantity versus a log of that quantity when you're treating things like text characters for your ranges?
So the question is about encoding the parameters. Does it matter if it's a regular quantity or a log of a quantity? In fact, one of the quantities we encode in the log rather than the raw number, because it spans a wide range of values. And no, it doesn't seem to matter. Basically, you just have to fine-tune it to try to optimize the efficiency on a case-by-case basis. I don't think there's a general prescription that would allow you to know a priori whether or not it's going to work in a specific case without just trying it.
Are there any lessons that you've learned from modeling the sun when applying it to the Kepler project, or will all the data be thrown away?
So the question is, did we learn anything from the sun that might help us with the Kepler project? Helioseismology, seismology of the sun, has provided those lessons basically for 20 or more years. And what's happened as a result is that our models of stars like the sun have been extremely well calibrated for this one specific case. So we know from experience that kind of improvement in the models is possible with these types of observations, and now the task is to just do that at many different physical conditions and many different ages for stars. So we have calibrated at a single point, and now we need to calibrate the models at all these other points.
Will the data be available online for other people to play with it, try to model?
The question is, will the data be available online? Yes, there's a specific timeline for Kepler data to become public. Because of the planet hunting nature, the timeline for that is longer than some people would like, but the people who've been working on the mission have been working on it for a very long time, so maybe that's appropriate. The astroseismic part of it, I think, will be done as openly as is feasible. That seems to be the pattern so far. Any other questions? Thanks for coming.